Welcome to your premier destination for mastering concepts. Crack IIT, NEET, and all board exams with us.
Picture a cyclist approaching a sharp, sweeping curve at high speed. They have a fraction of a second to get the entry right. To navigate any circular turn, physics dictates a requirement for centripetal force, an inward pull toward the center of the curvature. If the rider attempts to execute this turn while remaining strictly upright, perfectly perpendicular to the ground, the physics of the system breaks down. Look at the forces. With the rider vertical, ground reaction pushes straight up through the center of gravity, while tire friction pulls inward at the base. These misaligned forces create an unbalanced outward torque, twisting the rider away from the curve. This torque sweeps the bicycle outward from underneath the rider, leading to an immediate loss of control and a wipeout. Surviving a high-speed curve depends on neutralizing that outward torque before it overcomes the bike's stability. To stay upright, the rider must lean inward at angle theta, measured from the vertical reference. By leaning, the total ground reaction force, the blue vector R, tilts inward, aiming directly through the rider's center of gravity. Because this tilted force now aligns with the center of gravity, the twisting torque is eliminated. The rider enters a state of dynamic equilibrium. This lean is a structural requirement, realigning invisible force vectors to keep the bike from flipping outward. That single tilted reaction force is actually performing two distinct physical tasks simultaneously. The first task is counteracting gravity. This is handled by the vertical component of the reaction force, labeled R cosine theta. As the equation for vertical equilibrium shows, this component perfectly balances the combined weight of the bicycle and the rider. The second task is generating the turn itself. This comes from the horizontal component, R sine theta. This horizontal force provides the inward centripetal acceleration necessary to maintain the circular path. By leaning into the curve, the cyclist uses the ground itself to generate the exact inward force needed to turn. By dividing the turning requirement by the gravity requirement, we find the master equation for the perfect lean angle. One of the most striking details here is what is missing. The variable for mass has canceled out entirely. A heavy adult and small child must lean at the exact same angle to take the same turn at identical speeds. Speed is the most influential factor in this equation. Because the velocity is squared, even small increases in speed demand significantly more lean. Doubling your speed through a curve doesn't just double the requirement, it necessitates a fourfold increase in the tangent of the lean angle to stay balanced. But there is a physical limit to this lean. Eventually, the required horizontal force exceeds the maximum friction the tires can provide against the road. This defines the maximum safe cornering speed. At this threshold, the pavement's friction coefficient can no longer hold the bike on its path. The leaning cyclist operates at the intersection of these variables, constantly adjusting for speed, the curve radius, and tire grip to maintain the balance required for dynamic equilibrium.
Thank you for exploring the universe with us. Subscribe to Fundamental Physics for more.